In this next section, section 5, we discuss open problems in cosmology. This is actually, in a sense, somewhere between quantum mechanics, quantum theory, and general relativity. There are lots of very interesting problems in theoretical physics, and also there are some precise problems in mathematical cosmology, mathematical physics. Here's a couple of problems or topics of interest discussed a little bit, but I think it's widely taken that the biggest theoretical problem in cosmology is the existence of dark matter and dark energy. In the models, one looks at very simple models and try to find out what the predictions for observations are. And it turns out in order to match the models with observations, one has to postulate the existence of certain types of exotic matter. Dark matter, which is not seen in the sense that there's no radiation, electromagnetic radiation that is emitted that we can see, but it does act gravitationally, so we can know its presence through the dynamics of, say, for example, galaxies and so on. Dark energy is even more exotic in the sense that not only can you not see it, it has no gravitational effect. Dark matter is widely believed to be that it will be resolved with traditional physics, maybe a new particle, a change in the differential equations, an alternative theory. Dark energy is a real puzzle, and there's no really good ideas out to describe how that the dark energy problem can be resolved. This is said to be the most important problem in cosmology by Steven Weinberg. The problem is that if there is this constant dark energy that is posited, then the only estimates of it would come from quantum gravity, in which case it would be much, much bigger than what is necessary for cosmology, to solve the cosmological problems. There's another aspect of cosmology called inflation. This is the idea that in the early universe there was a period of accelerated expansion that helps resolve some of the technical problems in cosmology. The existence of inflation, that is, a period in which the universe begins to accelerate, has been studied within very simple cases, but there's no proof that in general a period of inflation would take place. Now, I mentioned both of these topics, dark energy and inflation, for a particular reason. This is a little bit more explanation about the inflation problems, and that is, in both cases, a classical solution of GR again is going to play an important role. This is the so-called de Sitter spacetime. This is the analogue of anti-de Sitter with a positive cosmological constant. In the case of dark energy, if there's a cosmological constant acting as the dark energy, or something like a cosmological constant, then we would like de Sitter spacetime, which represents the asymptotic behaviour of this spacetime, to be stable. Similarly, in the case of inflation, in the early universe, the universe undergoes a period in which it's approximately de Sitter. So again, de Sitter space, the stability of de Sitter space is important in studying models of inflation. Namely, if it's not stable, then perhaps inflation is not likely to occur, and the theoretical idea, the model, the paradigm, is not valid. So the question is what is the stability of de Sitter spacetime? Again, we have, this is based on general relativity, a set of differential equations, and problems like proving the stability of a particular equation, a particular solution, is a well-posed problem within general relativity. So some very simple results have been known for a long, long time, talking about the stability of de Sitter. So there are various theorems and results which are kind of summarized there. These theorems may apply to the case of de Sitter at late times, i.e. in models of the late universe with dark energy, but they don't necessarily apply in the early universe in the case of inflation. Namely, there isn't a theorem that says with particular initial data, generic initial data, with certain assumptions about the matter fields, that the models will necessarily accelerate. This is called the cosmic no-hair problem, and trying to prove the stability of de Sitter in the general case of inhomogeneous data is an unsolved problem. So one problem that's of importance is proving the stability of de Sitter for generic inhomogeneous data. Secondly, again, because the equations are represented by differential equations, we can have particularly rigorous conjectures in various contexts. In cosmology, what we have is it's the situation where the model is evolving with a matter distribution representing the matter in the universe. The singularity theorems tell us that in the cosmological context there's an initial singularity, that is, in the past. But the singularity theorems say nothing about the nature of what the models look like as you approach this past singularity. So the next question is, what is the generic behavior of Einstein's equations as you go to the past towards the singularity? Now the Russians, BKL, have done some very good work and shown that within, qualitatively shown, not rigorously proven, that for general initial data, the approach to the singularity has certain features. It's vacuum dominated, that is, the matter's not dynamically important. It's local, that is, local means its behavior at different points might be different, and oscillatory. Models actually oscillate, and the dynamics are referred to as the BKL dynamics. This oscillatory nature is actually a realization of something called chaos in dynamical systems, and so the universe itself is chaotic in its dynamical behavior as you go back towards the initial singularity. Now, the BKL conjectures have been proven, have been analyzed locally using qualitative methods, and there's an argument that in the spatially homogeneous case, spatially homogeneous means that there's no spatial variation, so the PDEs of GR become ODEs, and you can use various techniques such as dynamical systems to study the qualitative features of these models. They've shown that in the case of spatial homogeneity, the BKL dynamics is typical. There's an open class of open set of initial data for which this occurs. What is lacking is rigorous proofs of these conjectures and generalizations to the case of general inhomogeneous initial data. As it says here, the rigorous proofs have actually only been obtained rather recently, and they're not complete. They're not completely. It's not completely solved in the spatially homogeneous case. So one of the problems is to actually prove rigorously that the past attractor of the general spatially homogeneous models is described by the BKL dynamics, which is termed the mixed master attractor. There's a few comments about what results have been proven. and more importantly, to prove something in the inhomogeneous case. This is basically uncharted territory. Prove the general behavior, dynamical behavior, in the spatially inhomogeneous case, the general case of models evolving towards the past singularity. There's another problem that is particularly of particular interest to me, that I'll include in this category. That is, how do you average a tensor on a differentiable manifold? This question has not been solved. There is no covariant and gauge invariant way of averaging a tensor. Now, there's the mathematical aspect, that is, how do you define averaging, coarse graining on a differentiable manifold. There's also the application. Now, if we have a situation where we have general relativity with matter perhaps defined on an interesting scale like astrophysical scale, the matter is going to be inhomogeneous. There's going to be objects like stars, galaxies, and so on. So the matter distribution is not smooth, not spatially homogeneous. If we take those equations defined on those scales and average, we then get a coarse-grained version of Einstein's equations, which would be appropriate on large scales, in which cosmology is important. And the question is if we coarse-grain the equations, because Einstein's equations are nonlinear, when we coarse-grain the equations, Einstein's equations, to find appropriate dynamic equations on large scales, do they have any additional terms? Are there any extraneous terms that appear? And if so, what would their effect be on cosmological observations? The first part of the question is defining tensorial objects on a differentiable manifold, is certainly mathematics. The second part, to look at the interpretation of averaging, is a problem in physics.